Hello friends, so today we will prove that ZP star is grouped under multiplication modulo P. So this is the operation we are defining on this set ZP star. So first of all, let's see what is ZP. So ZP is the integers modulo P. And what is integers modulo P? It is the set of remainders when numbers are divided by P. So when any number is divided by P, so what are the possibilities of remainders? So it will be 0, 1, 2, 3 up to P minus 1. So ZP star, from this set I am just excluding 0, okay, and here P we are considering that it is prime. Now we will prove that the ZP star is grouped under multiplication modulo P. So first of all, let's prove closure property. For that, we'll choose any two elements from this set, and we will prove that this product is also there in this ZP star. So what is the operation we are defining on the set? So X multiplication modulo P. So two elements we are taking, and what is the operation on them? So I am multiplying both the number and then I am dividing it by P. Whatever is the remainder, that is the result. Okay. So if I am choosing any two elements from this set X and Y, and I am dividing it by P, so definitely the remainders will be from this set only. So only the number which is not present in this set is 0. Okay, if remainder is 0, that means P will divide X and Y, P will divide this product XY, but this is not true because both X and Y is from this set, and both X and Y is less than P, in fact I can say. So if P divide P, and also P is prime, and if P divide XY, it means that one of X or Y, is multiple of P, then only it can divide this product. Okay, so which is not true because neither X nor Y is multiple of P. Therefore this product will never leave remainder 0 when divided by P. So definitely XY will belongs to the product, XY will also belongs to ZP star. So closure property is satisfied. Next is associativity. For that, we'll choose three elements X, Y, Z from the set ZP star. Clearly the grouping will not affect the operation. Right? So it will always follow this thing for every X, Y, Z from the set ZP star. Now identity. For identity, definitely 1 is the identity element in ZP star. Okay, because for any X from the set ZP star, it will hold this thing, right, for all X. So 1 is the identity in ZP star. Now for the fourth inverse, fourth is existence of inverse. And also that identity element should be unique. So definitely identity is unique here. 1 is unique. Now next is existence of inverse. So let X from ZP star, we will find its inverse. Okay, and also we will prove that inverse of X is unique. So for that, I'm constructing a new set like this: X, 2X, 3X, 4X, up to p minus 1 x. Okay, x is any element from zp star. That means x is greater or equal to 1, less or equal p minus 1. Now my claim is no two numbers. Now my claim is no two numbers in set S leave the same remainder, and definitely no definitely no numbers leave remainder 0, and the argument is same. If any number is leaving remainder 0, so that means p divides that number. Say p divide ix, and where I is also less or equal p minus 1, greater or equal 1. So if p divides this number, this product, so definitely one of them should be multiple of p, which is not true. Hence no numbers leave remainder 0, and also I am claiming no two numbers in S leave the same remainder. So let's prove this claim. Suppose there are two numbers in this set S which is leaving the same remainder. Suppose ix and jx leave the same remainder. That means when p divides ix and jx, then they both are leaving the same remainder. Okay, hence I can say that ix is congruent with r mod p and jx is congruent with r mod p, right? Or I can say that ix is equal to pk1 plus r and jx is equal to pk2 plus r. For some, k1 k2 belongs to integers, right? k1 and k2 from set of integers. Okay, so if I'll subtract, so what I'll get, ix minus jx is equal to p k1 minus k2, and just let's assume that I is greater than j. Okay, so what I'll get, so I'll get that p divide I minus j into x. It means that p divides I minus jx. Again the same argument, if p is dividing this product, so one of them has to be multiple of p because p is prime, which is not true, right? Because x is not multiple of p, because x is definitely less than p we are having, and also I and j both are less than p we are having, so their subtraction will also be less than p, so it can't be multiple of p. Okay, so we are getting the contradiction that there exist two numbers which are leaving the same remainder. Hence our claim that no two numbers in S leave the same remainder. Okay, so the remainders are 1, 2, 3 up to p minus 1. Is the remainder set of S. Okay. Now if x is 1, then S will be same as P star, and 1 is itself inverse of its 1, and 1 is inverse of itself. If x is p minus 1, then p minus 1 square is equal to p square minus 2p plus 1, and when it is divided by p, then it will leave remainder 1. Okay, therefore p minus 1 square is congruent with 1 mod p, hence p minus 1 is also inverse of itself. Note that no other numbers from Zp star can be multiplicative inverse of p minus 1. Why? Because this set S, in this set S, no two numbers leaves the same remainder, that we have already proved. Hence p minus 1 has unique multiplicative inverse. Right? And similarly, when x is other than 1 and p minus 1, then it will have unique multiplicative inverse, that we can prove. Hence Zp star is grouped under multiplication modulo p.